It was one of the most remarkable missions of all time. In November 2014, the spacecraft Rosetta arrived in orbit around Comet 67P, Cheremeov-Gerasimenko. It spent more than 2 years studying the comet, releasing the Philae lander onto the surface, and aiming its suite of instruments at the nucleus as it followed its orbit around the Sun. But now, 5 years after it went into orbit, the Rosetta mission is coming to an official close, and the scientists behind it have gathered here in Holland for one final meeting. And we've come to find out what this iconic mission told us about Comet 67P. Welcome to the Sky at Night. This is ESTEC, the European Space Agency's Research and Technology Centre in Holland. It's here that ESA's missions are dreamt up and their spacecraft designed. And it's here that Rosetta's mission scientists are gathering. For the last 5 years, the team have been poring over and puzzling over the data returned from Rosetta's instruments. And now, it's finally time to find out what we've learnt from this most remarkable mission. The results being presented here are set to transform our understanding of comets. But to find out why this mission was so important, the first person I wanted to catch up with was project scientist Matt Taylor. We're here once again to talk about Rosetta. Can you remind us what Rosetta's main goals were when you set out?
Scientifically, comets are linked to the origin of the solar system. They are the building blocks of the solar system. So we wanted to study the makeup, how the comet was put together to give us an idea of where it came from, and that constrains how the solar system was actually before the sun was formed. In addition, we wanted to use the mission to understand how comets themselves work, how it is that as they approach the sun, they become more active and these hundreds of thousands of kilograms of material are ejected. How does that happen? So these were the drivers for us doing the Rosetta mission.
And that, I guess, dictated that you needed to go to a comet, you needed to follow along with it, which is the unusual Rosetta thing, and ultimately try and land on it.
That's what it was all about, and it was quite difficult.
Not everything went perfectly. One of the most exciting phases of the mission came when, shortly after arriving in orbit, Rosetta released the Philae lander down towards the surface. We were in mission control as the team nervously waited for confirmation of touchdown. But the feeling of triumph was short-lived. Rather than touching down softly and anchoring itself to the comet, it seemed Philae had bounced across the surface. A picture returned from its camera showed that it had ended up lodged against a cliff. With its solar panels shaded from the sun, it soon ran out of battery power. People still talk about Philae, the little bouncing lander. That was such an important part of the mission.
Yeah, it was. We dealt with it and thought of it as like the cherry on the top of the mission itself. And although it had this unintentional journey across the surface of the comet, it still gave us fascinating insight into that spot where it landed. About 80% of the operations that we wanted to carry out on the surface were carried out, so that's pretty good, given where it was in a ditch.
But while Philae was stranded on the surface, the Rosetta spacecraft spent 2 years orbiting 67P, its suite of instruments harvesting huge amounts of data. Data which is still being analysed. Last time I talked to you at the end of the mission, we talked about it being the end of the operational mission because the spacecraft had landed on the comet. But I think you said it was the start of the scientific mission because people could concentrate on making use of their data.
Absolutely.
How much work has been done?
it's difficult to quantify. I know
Yeah.
at the time there was a nice example of showing a jigsaw puzzle of the Rosetta Stone and saying, well, we've got all of the data and maybe we've put 15% of the puzzle together. Maybe now we're at 25, 30%, but then what we're seeing, because we're scrutinising the data, is that maybe there's a couple of different puzzles that are being put together, and that's
the same box.
Yeah,
on the
exactly.
same
Yeah,
time.
you can make 3 different versions of the Comet with the same pieces. So that's where we are.
People will be arguing about this data in 10 years' time,
Absolutely.
for sure.
Yeah, absolutely.
Rosetta has been an incredibly impressive project. It's taken 30 years, cost £1 billion, and produced data that the scientists will be analysing for years to come. But what is it all in aid of? Why are the solar system's smallest bodies, comets and asteroids, so interesting? We asked meteorite expert Tim Gregory from the University of Bristol to explain.
One of the reasons that we study the asteroids and the comets is to understand how our cosmic home, the solar system, formed, how it transformed from a giant cloud of interstellar gas and dust into the clockwork-like system of planets that we see today. It's a process that took an incredibly brief period of time, just 10 million years.
To investigate this period, we need to observe the bodies that formed at that time. One way to study them is by using spacecraft like Rosetta.
But another way that we can study them is by looking at the rocks that originate from them, the meteorites.
These unremarkable looking fragments can tell us a huge amount about the formation of our solar system, because they're incredibly old.
What we're looking at here is one of these white fluffy objects in a meteorite, but imaged under a scanning electron microscope. They're called calcium aluminium rich inclusions, or CAIs, and on this image, the red parts of the image are the aluminium and the blue parts are the calcium. CAIs are really strange objects. They only really form at incredibly high temperatures, 1500 degrees C or more. And the only place in the solar system where it gets that hot is right next to the sun. This means that the CAIs must have formed in the inner solar system right next to our star. But that's not the only interesting thing about CAIs. We can actually date these objects to find out how old they are. And it turns out that almost all of the CAIs have the same age, 4,567,000,000 years old. These are the oldest things that we've ever dated.
Because they are so old, we use the age of the CAIs to define the start of the solar system. The formation of these minerals is time zero, the moment the solar system began. At that time, the solar system was made up of a protoplanetary disk, a swirling cloud of gas and dust. The first solid bodies to form in that cloud were the asteroids and the comets. And the fragments of them we find in collections like this one in the Bristol City Museum can tell us a great deal about how the solar system formed.
This is an iron meteorite, and it's incredibly heavy. It's like nothing else that you'd usually find on the Earth. This rock formed in the first 1 or 2 million years of our solar system's history. It comes from an asteroid that melted, and the reason it melted is because the dust from which this asteroid coalesced contained vast amounts of radioactive isotopes. And as these isotopes decayed, they melted the asteroid entirely. The dense elements like iron and nickel sank to the centre of the asteroid to form a giant molten metallic core. And over the next 10 to 20 million years or so, this metallic core cooled and crystallised to form the metallic iron meteorites. We think that the same process of core formation that happened on the asteroids also happened on the Earth. So by studying the shattered fragments of these long dead worlds, we can learn more about our home planet, the Earth.
But not all meteorites are the same, and by analysing the differences between them, we can reveal the structure of the early solar system.
We know that the CAIs formed right in the heart of the solar system, next to the red-hot surface of the early sun. And throughout the inner solar system, asteroids were forming, like the parent worlds of the iron meteorites. But it wasn't just the inner solar system. Worlds were forming everywhere. And the traditional view held that in the inner solar system, those worlds were dry where the temperatures were high, and they formed from rock the asteroids. But in the outer solar system, things were much colder, and the motes of rocky dust coalesced alongside water ice to form water ice-rich objects, the comets. So we had a clear distinction. We had rocky objects in the inner solar system and the icy comets in the outer solar system.
But some remarkable discoveries have shown us that this traditional view is far too simplistic. Exactly 50 years ago, a meteorite fell on the Australian farming village of Murchison. It came down as a fireball that showered the town with stones, like this one.
This is a piece of the Murchison meteorite. It's completely unlike the iron meteorites, and that's because it comes from an asteroid that never melted. And because that asteroid never melted, the dust from which it coalesced was preserved.
But although it looks like a rocky meteorite, this stone also contains large amounts of water bound up in the mineral structure. And that is a feature we associate not with asteroids, but with comets.
It probably formed out here, beyond the orbit of Jupiter, where it was cold enough for water to form without being boiled away by the heat of the sun. The parent asteroid of the Murchison meteorite coalesced from a mixture of rock and water, so it shows that the distinction between rocky asteroids and icy comets is far too simplistic. Some worlds were a mixture of the two. We had asteroids with comet-like features and comets with asteroid-like features.
But it's not just the water content that makes the Murchison meteorite special.
The locals who rushed to the scene of the fall just after the Murchison meteorite had landed reported a strong smell in the air, something a bit like paint stripper or a petrol station. These were organic molecules leaking from the stone into their surroundings. Carbon-based chemistry, the molecules of life, leaking from a meteorite that had just fallen from outer space. So by studying the meteorites here in Earth-bound laboratories, we've learned not just about the formation of our solar system, but we've also perhaps learned about the origin of life on Earth itself. And that is a story that each one of us is a part of.
Studying meteorites that have fallen to Earth can tell us so much. But they can't tell us everything about the solar system's small bodies. Icy comets don't survive the journey to the Earth's surface, and so we need to study them in their natural habitat. As Rosetta approached the comet, it revealed the surface of another world covered in cliffs and pits. One of the key goals of the mission was to study how 67P changed on its journey round the solar system. We expected that as it approached the Sun, it would heat up and begin to emit a cloud of gas and dust particles. But the power and the scale of the activity that Rosetta revealed took everyone by surprise, as I discovered when I met Rosetta imaging scientist Michelle Kuppers. What exactly are we seeing here?
Well, we're seeing the surface of the active comet. We're seeing lots of dust particles, and many of the dust particles we are seeing here have been ejected elsewhere and are now falling back to the surface.
So that's this sort of snow that's coming down.
If you want, it's kind of snow. Also, it's mostly dust what we are seeing here.
But I think people might think this is a camera effect, but all of these dashes and dots, those are dust particles.
Those are all dust particles,
lit up
yes.
in the sun.
Yes.
Yeah.
It's not kind of powdery dust, micrometer-sized dust, but it's really big particles, centimeter, decimeter-sized particles. We didn't expect so many large dust particles that you can really see them individually in the images.
Yeah. These dust particles are up to 10 centimeters across, so big that as 67P reached its closest approach to the Sun, the spacecraft had to be maneuvered away from the comet. From that safe distance, it observed much larger objects being blasted from the surface. What are we looking at here?
So this is a big boulder that started at the comet, that has been ejected from the comet, and as we can see here, at least temporarily, it went into orbit around the comet.
So people are calling this a moon of the comet.
Yeah, it's nicknamed Chury moon. Well, it's let's say a temporary moon. So we have not yet been able to follow its fate for the full time it was there, but it orbited the comet for at least 2 days. However, such an orbit is not stable, so we would expect it at some point either to fall back or to escape the comet.
Is this a rock I could lift, or is this something the size of a house? I don't really have a sense of scale here.
From its brightness, we have estimated its size, and it's the biggest particle we have seen so far. We estimate it to be 3 or 4 meters in diameter. It's quite substantial.
No one expected that the comet would be capable of ejecting boulders of this size. It's now thought that they're knocked off by the powerful outbursts that have been seen erupting from the surface of the comet. But the source of those outbursts was also something of a mystery. A clue emerged when pictures of the surface of the comet revealed dramatic changes over time. Cliffs that had collapsed in the areas where the outbursts were thought to come from.
We now see correlations between outbursts and collapses of those cliffs. So for those cliffs, we never have seen one collapsing, but we have seen from the before-after states that the cliffs were collapsing. And then sometimes we can trace back the outbursts to the locations on the surface where this happened, and the whole picture is consistent that at least some of those outbursts happens when those cliffs collapsed. And this, of course, liberates subsurface ice to the surface, and this then causes those outbursts.
So when we think of this amount of activity, collapsing cliffs and outbursts, and plus the regular activity, I start worrying about the comet, right? Is it going to run out of material?
No, not anytime soon. So we estimate that the surface layer that is lost in a perihelion passage is of the order of 1 meter.
Okay.
While the comet, the diameter of the comet is around 4 kilometers, so it can survive quite some time from that point of view.
So it'll be around for a while, but nonetheless, if we want to understand comets, we have to understand how this activity works, and it's clear we don't know the details.
That's right. I mean, we know the basics, which is that the ultimate source of energy is the sun. The ice sublimates and it takes the dust with it. But the details of this process are not really well understood here. And this is something we're also still working on, and where we got lots of new information from the Rosetta mission.
Well, the best missions always ask more questions than they solve. So thank you for coming and asking some questions, and thanks for bringing Jeremiah Gerasimenko to us. The remarkable increase in activity that comets go through as they approach the Sun is not just of interest to Rosetta's scientists. It is that same phenomenon that's made comets so fascinating to stargazers for thousands of years.
Although comets are among some of the darkest objects in the solar system, not dissimilar, say, to the darkness of a lump of coal, when they get close to the Sun and become enshrouded in a huge cloud of gas and dust, they can become one of the brightest objects in the night sky. Now later on, if the clouds clear out of the way, I'm going to be looking for a comet with the aid of this telescope. But you don't always need a telescope to see comets. The most spectacular ones can be seen with the naked eye. They are among the most awe-inspiring sights in the night sky, and some are so bright they can even be seen in the daytime. One of my favourite comets is called C2006 P1 McNaught. Now this got really bright at the beginning of 2007. And I managed to take a photograph of it in the one day of clear weather we got around that time. And you can clearly see the head of the comet and the tail stretching back up through the sky. Now the comet then headed south and put on a spectacular show from the southern hemisphere. And you've got this structure which is visible in the dust term. Now that results from the nucleus rotating, and as it's doing so, it's venting out material. So it creates these striations in the tail. When you see a comet like this that suddenly appears, its tail streaking across the sky, it's easy to see why they used to be seen as messengers from the gods. Halley's Comet appears embroidered on the Bayeux Tapestry, a warning of the Norman invasion of Britain in 1066. Roman coins from the 1st century BC record a very bright comet that appeared shortly after the assassination of Julius Caesar. It was believed to be his soul transformed into a deity. Nowadays, of course, we have a more scientific understanding of comets and their tails, but they are no less interesting. There are two main types of tails which are associated with comets. This is a photograph of comet Hale-Bopp taken from early in 1997. As the solar wind passes the comet, so it draws charged particles, ions, from the comet's head back into a long, thin, straight tail, which is known as the gas or ion tail, and that points directly away from the sun. Now, the light from the sun also has a force associated with it. That's called radiation pressure, and that pushes on the dust particles and it pushes them away from the sun. This gives them larger orbits, which are also slower. So the dust particles fan out into this beautiful curving, what's called a dust tail, and that typically looks quite yellowish in colour.
We only get a good naked eye comet every 10 years or so. So the rest of the time, if you want to see a comet's tail, you'll need a telescope and clear skies.
There are always lots of comets up there in the night sky. Most of them are really, really faint. But if you want to find out about them, there are lots of resources available on the internet. The British Astronomical Association, for example, has a list of comets currently visible. Or you can download apps which will show you where comets are in the night sky. So just pick one which is in a good position for your location and see if you can see it.
The comet that I'm going to try to image is called C2018 N2 Assassin. It is visible throughout November in Andromeda, a constellation which spreads out of the northeast corner of the Great Square of Pegasus. You'll find it north of the eastern side of the Great Square, tracking towards the west throughout November. Over the coming days, it will be above the horizon all night and will be due south around 9 p.m.
So basically I've got the camera attached to the end of the telescope and I've pointed the telescope at a bright star so that I can get the camera accurately focused, and then once I've done that I can turn it onto the faint comet and we'll see what we get. So I've got a picture of the comet. You can see the sort of fuzzy head and you can see the tail heading back towards a little pattern of stars. Now on my smartphone app, there's the comet's head with the tail heading back towards this little pattern of stars here. That's double confirmation it is the right object. So I'm very pleased with that. We've got a real live comet tonight.
This is how we've seen comets for thousands of years, diffuse streaks traversing the background of the stars. Now, thanks to Rosetta, we can really appreciate the complexity of these worlds. But although the images were the most striking feature of the mission, the most exciting results came from a mass spectrometer called Rosina. Its purpose was to sniff the vapour and dust coming off the comet, to identify what other substances are lurking amongst the rock and ice. It found hundreds of different molecules. To try and make sense of them, Swiss astrophysicist Katrin Altweg has organised them into a chemical zoo. Why are we standing in front of a bunch of animals?
That's because I'm actually a physicist, not a chemist. And I always have problems with remembering the names of the molecules we detected. So I had to associate them to animals in order to remember.
And here we are. So this is the zoo of gases that were detected. Where do we start?
Let's start with the butterflies.
Okay.
These are the very volatile molecules we found in the comet, which also shows that the comet was formed very cold.
These are molecules that would just break
disappear,
down if they were heated
or
up.
never condense in the comet. Then we have the funny animals, the alcohols.
Yeah.
Then, of course, the tall giraffes, which are long carbon chains. So we have the elephants, which are aromatic ring compounds, so with C atoms. Then the salty beasts, these are the halides.
And we've got the lion up here. This is glycine. Why is glycine so exciting?
Well, glycine is the most simple amino acid. Amino acid is part of all life on Earth. We have it in the DNA, we have it in the cells. We need it. Without amino acid, no life. And to find that extraterrestrial glycine tells me that all building blocks of life were there before the solar system started.
We've known that space is full of organic molecules for years. But Katrin has found a crucial piece of evidence that shows how the organic molecules on comets like 67P may have helped kickstart life on Earth. And it comes from another ingredient that she found on the comet, the element xenon.
Xenon is a very interesting atom because it has 9 stable isotopes. And the relative abundance of these isotopes is a fingerprint of where they come from. And the strange thing is that our Earth has 2 xenons. We have xenon in the Earth's mantle, in the interior, and we have xenon in our atmosphere, and it's not the same xenon.
So they must
It's
have
not
come...
the same fingerprint.
Okay, so the xenon that's in the core of the Earth came from one place, and the xenon in our atmosphere came from somewhere else?
Yes.
The xenon in the Earth's mantle is a perfect match for the xenon fingerprint that we find in meteorites. But until now, the source of the xenon in the Earth's atmosphere has been a mystery.
So for 40 years, people were actually looking for this special xenon, which we have in the atmosphere. And with 67P, we found this missing xenon. And from the composition of the comet, from the composition of our Earth's atmosphere, we can deduce that about 22% of our terrestrial atmospheric xenon is from comets. And we know how much xenon there is in a comet, and from this we can say how many comets must have hit the Earth.
I can't even begin to guess how many comets.
You need about 100,000 comets.
That seems like quite a lot of comets.
Yeah, that's true, but if you look at the moon, you will see it has many craters, and these craters all have the same age, 3.8 billion years. At that time, there was what it's called late heavy bombardment. So a lot of small bodies hit the moon and of course the Earth. And that's when the 100,000 comets could have hit the Earth.
And the result of something that happened 3.8 billion years ago affects the air that we breathe now.
Exactly.
This discovery would have been exciting on its own. But crucially, as well as bringing xenon, these 100,000 comets would also have brought billions of tons of organic molecules, the raw ingredients for life.
And it's interesting because about 100 million years after this late heavy bombardment, we had life on Earth. Single cells, but it was life. So this might not be an accident.
Yeah. So the stuff of life might have come from comets like 67.
Might have sparked life.
Interesting.
It did not bring any animals.
No, they came later. Well, thank you for telling us about the zoo, and we'll look forward to seeing what else is in there over the next few years. Thank you very much. So, this is it. This party marks the official end of the mission, but it's not the end of Rosetta's amazing story. The data stored in its archive will keep comet scientists busy for decades. Rosetta will answer questions that we haven't even thought of yet. And I reckon Comet 67P has a few surprises left in store. Good night.
The beauty, fragility and danger of life on Earth through each of the continents. David Attenborough's 7 Worlds, 1 Planet, streaming now on BBC iPlayer. And tomorrow on BBC4, tiger sharks, whale sharks and green turtles on the Great Barrier Reef at 8.